Hello everyone, I'm Heng Zhang. I'm glad to present our work named Guided Attentive Feature Fusion for Multispectral Pedestrian Detection. This is a joint work with Elisa Fromont, Sébastien Lefebvre from IRISA Laboratory and Bruno Avignon from Adames Company. Why do we need multispectral images for pedestrian detection? Thermal and visible cameras have different imaging characteristics under different conditions. For example, visible cameras provide precise visual details such as color and texture in a well-lit environment, while thermal cameras are sensitive to temperature changes, which is extremely useful for nighttime or shadow detection. Thus, multispectral image pairs provide complementary visual information, making pedestrian detection systems more robust and reliable. An adaptive fusion of thermal and visible features should take such complementarity into account and should locally identify and leverage the information from the most relevant modality. In this work, we focus on the multispectral pedestrian detection task. Nowadays, deep learning-based methods, more specifically two-stream convolutional neural networks, largely dominate this field. A typical two-stream pedestrian detection network consists of two separate spectral-specific feature extraction branches, a multispectral feature fusion module, and a pedestrian detection network operating on the fused features. In this paper, we propose a novel and fully adaptive multispectral feature fusion approach named Guided Attentive Feature Fusion. It consists of two components: intramodality attention module and intermodality attention module. The former highlights features of an area with a pedestrian, the latter adaptively select modality with superior image quality. More specifically, in intramodality attention module, thermal or visible features of an area with a pedestrian are highlighted by multiplying the learned features with the predicted pedestrian mask. In intermodality attention module, an intermodality attention mask is predicted based on the combination of thermal and visible features. The predicted mask has two values for each pixel, corresponding to the weights for thermal and visible features, and its ground truth value is defined according to the comparison between error masks from thermal or visible intramodality attention masks. We conduct experiments on KAIST Multispectral Pedestrian Detection Dataset and FLIR Dataset to evaluate the effectiveness of the proposed method. KAIST Dataset contains 7,601 training image pairs and 2,252 pairs for testing. The aligned FLIR Dataset contains 4,129 well-aligned multispectral image pairs for training and 1,013 pairs for testing. It covers three object categories: pedestrians, cars, and bicycles. Here we show some experimental results on KAIST Multispectral Pedestrian Detection Dataset. For different backbone networks or annotation settings, both inter- and intermodality attention modules consistently improve the baseline detection accuracy, and their combination leads to the best detection under all experimental settings. We also prove the necessity of guidance by introducing a reference experiment where guidance is removed, which leads to serious degradation of performance. Experiments on FLIR Dataset show that the average precision is improved for all intersection of union thresholds, which demonstrates that our method can generalize well to other different types of images. We also report the total number of learnable parameters and the average inference runtime on two different computation platforms. From the table, we can conclude that the additional parameters and the computation cost from GAFF is low, which means less than 0.1% of additional parameter and around 1 millisecond of inference time. We then provide visualization results of intermodality, and the hybrid attention masks during daytime and nighttime. For intermodality attention masks, it appears that the guided attentive fusion tends to select visible features on well-lit areas and brightly colored areas, and to select thermal features on dark areas and uniform areas. Note that these attention preferences are automatically learned via our intermodality attention guidance. That's all. Thank you for your attention.